Okay, so this is some material from box D in unit 5.6. We're going to look at the scalar equation of a line. And before we get into the actual equation of a line here, we've got to deal with a little bit of terminology here. First thing, what do we mean by a normal line? Well, a normal line is just a line that is perpendicular to some line that you're already given. So normal in this sense just means perpendicular or at a right angle to. So if we're talking about vector specifically, a vector perpendicular to another vector is called a normal vector, or often we just call it just by the word normal. So the symbol that we normally use, no pun intended, to be a normal vector is n with the vector symbol over it. Okay, so when you see that, we're talking about a vector that is at right angles to some other vector that we're interested in. So, for example, let's say we've got a vector equation of a line here. I'll use negative 510 plus t times, and we'll use 1, 5 as our direction vector. And let's say we wanted to find a vector that was normal or perpendicular to this vector that we have right here. The way we're going to do that is we're going to start with our direction vector. Our direction vector here is 1, 5. The normal vector has to be perpendicular to this direction vector. The easiest way to get a vector that is perpendicular to a vector that you're given is you take your x and your y component of the vector that you're given and you reverse them. So instead of 1, 5, I'm going to change that to 5, 1. And you make one of those two components negative. So I'm going to make my 5 negative. So if my direction vector is 1, 5, my normal vector, my vector perpendicular, is going to be negative 5, 1. And you can think of this, if you think back to grade 9 and all that work that you did with slope. If you've got a line that is going over 1 and up 5, that kind of gave us a slope of 5 over 1. If you wanted something perpendicular to this, you took the negative reciprocal. So you flip this over, you change the sign to negative. So that gave us a new slope of negative 1 over 5. So we're basically doing the same thing here. We are interchanging our x and our y, and we're changing the sign on one of them to make it negative. And we can always check that these two things are perpendicular by using our dot product here. So if we take our direction vector, dot it with our normal vector, we should get 0. Let's just check here. We got 1, 5 dotted with negative 5, 1. It's going to give us negative 5 plus 5, which is 0. Exactly what we expect. So that's the easiest way to get a vector that is perpendicular to some vector that you're given. Okay. Why do we go through all of this normal stuff? Well, as I've said down here at the bottom, we can use a normal to define a line. And that's kind of what we do with the scalar equation or the Cartesian equation of a line. So we'll just jump right to what this looks like here. The scalar or Cartesian of a line has the form ax plus by plus c equals 0. Now, where have you seen this before? Even before that. Even before that. Go way, 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 way back. Let me give you an example here. Let's say we've got something that is like 5x minus 3y plus 10 equals 0. Where have you seen a line written like that? Think back to grade 9. What did we call this in grade 9?
Y equals mx plus b.
That would be y equals something something. This was the other one that we used all the time. This one was called, it's called standard form. And you spend all this time going from y equals mx plus b to standard form, then standard form back to y equals mx plus b. And the point that we made at the time was that you never wanted it in this form. because you wanted it in y equals mx plus b form because you could get the slope and the intercept and it was a lot easier to work with. The advantage of having it in this form, which is scalar or Cartesian or standard form, is that these two coefficients here, a and b, on your x and y, if we turn them into a vector, that vector AB is the normal to that line. So in a sense, we're using this normal, A and B, to define this line here. Okay? So if this is our equation here, our normal would be 5, -3. 5, -3 is the normal. So this is kind of the significance of having something in standard form. Yeah.
So is that just the direction vector?
This 5, -3 is perpendicular to the direction vector. Okay? So it's at right angles to this line here. Okay. Sorry?
It's not a line equation, it's just the direction vector perpendicular.
This here defines a set of points, x and y, that create a line. Okay? So this here is just, this is just a vector. Okay? It doesn't define a line yet. It defines the direction that is perpendicular to the vector. To that line, yeah. Okay. Okay, so for example, this is the kind of question you might be asked to do here. Find the Cartesian equation or the scalar equation of the line, and you're given it in vector format. R equals 3, -4 plus t, 2, 5. First thing that we're going to want to do is we're going to start with our direction vector for the line that we're given. So what's our direction vector here for this one? Yeah. So this is 2, 5. To get our Cartesian equation, we need this normal to get these numbers a and b. So we want the normal to this line here. So if our direction vector is 2, 5, what's our normal going to be? Well, we want something perpendicular here, so we're going to interchange x and y and change one of these things to negative. So we'll have -5, 2 is our normal to this line that we're given. So right away, this is telling us what a and b are in our Cartesian equation. So let's start. I mean, we know our Cartesian equation is going to be ax plus by plus c equals 0. We know what a and b are, so let's put those in. All we need to do is figure out what this last coefficient, this constant c, is going to be. Well, the other piece of information that we're given from our vector equation is that the point 3, -4 is on the line. This gives us a value of x and y that has to satisfy this equation. So we can sub those in. I'm going to sub in 3 for x and -4 for y. Now I just have to simplify and solve this for c. So I get -15 minus 8 plus c equals 0, or c is going to be 23. And I'm done. I just have to write out my equation here. It's going to be -5x plus 2y. Substitute in this value for c, plus 23 equals 0. And there's my Cartesian, or my scalar equation.
So is that the same line as the one up there?
This is the same line as R up here, okay? Just in Cartesian form. So the other thing that you might be asked is to go the other direction. They give us the Cartesian form here, 4x plus 3 minus 10 equals 0, and we want to find the vector and the parametric equations for the line. The vector one, I think, is the easiest one to get first. So we'll start by trying to find that. And really, this is just the opposite set of steps that we did before. We know if this is our scalar equation, that our normal to this line is going to be, well, it's going to be what? 4, 3. So if our normal is 4, 3, what can we use as our direction vector? Well, it's got to be perpendicular to our normal, so we can use something like, sure. So that's half of our vector equation right there. That's our direction vector. Now all we need is a point that we know is on the line here. So let's just say that's what we're going after. Need a point on the line. Well, we've got this equation, 4x plus 3y minus 10 equals 0. How can we find the coordinates of at least one point that is on this line? Okay, yeah. We're just going to substitute something in there for x and figure out what y is going to be. So we can put anything we want in there for x. So what should we choose x to be here? 0 is pretty easy. So we put in 0 for x, we get 3y minus 10 equals 0, 3y equals 10, or y is 10 divided by 3. So that gives us the point on the line is 0, 10/3. So we just have to put these two things together. Our vector equation is going to be 0, 10/3 plus t times our direction vector, which was -3, 4. And that's our vector equation. And of course, you could have chosen x to be anything and gotten a different point that was on your line here. And you could have also chosen 3, -4 as your direction vector as well. Okay? And it would give you not the same equation of the line, but an equation that is equivalent. Now, once we've got our vector equation, how do we get our parametric equations? Who remembers this?
X equals 0 minus 3t.
Yep, we're just taking the x components, portions out, and our second equation is going to be plus 4t. Okay. And that's our parametric. Okay. All right. The last type of question that you're going to be asked, I think, involving scalar or Cartesian equations is you're going to be asked to find the distance from a point to a line. Now, in the past, I've gone through a big, long derivation of how you do this, but I think this time I'll just show you the formula here and kind of explain what it means. So you've got to imagine that you've got a line, okay, with this Cartesian equation, ax plus by plus c equals 0. And you're given some point, p, and you know the coordinates to that point, x1 and y1, we'll just say. When they want the distance from the point to the line, they want this distance along this line that is going to be perpendicular to ax plus by plus c. Now the textbook goes through a big long derivation of how you do this. It involves picking a point on here, drawing a vector between those 2 points there, doing the projection of this vector that you've just drawn onto the normal, et cetera, et cetera, et cetera. This is what you need to know and remember, is this formula right here and how to use it. Okay? And all this formula is it's our Cartesian equation with the coordinates of the point, x1 and y1 substituted in. We take the absolute value of that, and then down below here we've got the magnitude of that vector, that normal vector AB. Okay. So, sample question here. Find the distance from the point 4, -2 to the line 2x plus 7y minus 3 equals 0. We just need to know this formula here. This distance is going to be the magnitude of ax plus by plus c, all divided by the magnitude of a squared plus b squared. So let's start filling this in here. We've got 2x plus 7y, and c is minus 3. We want the absolute value of that. And this is all divided by the square root of 2 squared plus 7 squared. And for x and y, I'm going to substitute in 4 and -2. Now I just need to evaluate. So in the numerator, I'll have the magnitude of 8 minus 14 minus 3. In the denominator, I'm going to have the square root of 53. My numerator works out to be, let's see, 8 minus 14 minus 3 is -9 over root 53. And the whole point of taking the absolute value there is, just in case we get a negative here, because we want the distance from the point to the line to be always a positive number. So this will become 9 over root 53. And in some courses, they would tell you that you have to rationalize the denominator. I don't care. Leave it a radical down in the bottom. That's great, as long as you get that value there. Okay?